Thank you. Good afternoon, everyone. So I'm Khaled, and I'll be talking about our project on Med-Gemini with my very close collaborator, Wei-Hung. Before I get started, I just wanted to mention that this project was a very big collaboration across many teams, both at Google DeepMind and Google Research. So today we're talking on their behalf for this effort here. As many of you know, probably like for coming to this talk and being interested in medical AI, to do well across a broad range of medical tasks requires lots of different skills. So for one, clinicians need to have advanced clinical reasoning. So a lot of the times, a patient comes and there are lots of different patient variables, their symptoms, their social history, these different lab results and scans, and they need to kind of reason over the whole picture and then kind of incorporate up-to-date medical knowledge in order to have grounded and accurate clinical decision-making. Other than that, they also need to be able to interpret lots of different multimodal artifacts. So there might be things like health signals that are recorded by the patient, or different medical imaging, whether it's X-rays or MRI scans or CT scans, and even videos, whether they're instructional videos, surgical videos, and the whole spectrum of medical videos. They need to be able to kind of interpret all these different modalities. And it's not just about this interpretation. They need to have kind of effective collaboration skills when a patient comes in. They need to kind of take down their history, be able to communicate with them clearly, kind of build empathy and that rapport and trust building. So really a lot of different skills into doing well across a broad range of medical tasks. Being researchers at Google, we were really excited with the announcement of the Gemini models, which is one of the frontier family of AI models, for two specific breakthroughs. So one is that the fact that this was one of the first foundation models that was trained natively multimodal. So from the start, from pre-training and on, multimodal artifacts and data was always taken into account. So that was one capability that was differentiated from different LLMs. But also with Gemini 1.5 and on, we had this breakthrough with really long context, up to 2 million context length. So now these models can take into account lots of different kind of patient histories. If you're in the clinic and you come with multiple visits and on all the data and we know videos and images, they can be very long context. We thought, wow, these models may be very well situated to do well in the medical domain. So we got really excited about that and started looking at, well, how does Gemini do on medical benchmarks? How is its medical knowledge and reasoning? But we found out that while it did do well out of the box on a lot of different tasks, there were clear gaps in medical knowledge and reasoning. This project was kind of our first attempt at trying to understand how do we fill that gap, how do we get Gemini to be very performant for lots of different medical tasks. So Med-Gemini is this effort with specializing Gemini to the medical domain. And the first step in that is just inheriting all the great capabilities that come with Gemini, which is its advanced textual reasoning, multimodal understanding, and long context processing. But for each one of these capabilities, we have a different medical specialization. So we recognize that in order to achieve up-to-date information and the clinical reasoning, integrating web search and doing further training on clinical reasoning traces was really important. In multimodal understanding, even though Gemini was trained across a very broad range of data, medical data perhaps was underrepresented. So for that reason, we found that fine-tuning on specifically medical images was really important, but also perhaps adding customized encoders for completely new modalities, such as EKG signals or those types of modalities. We also found that in order to really bring out the long context processing, doing inference-based algorithms like chain of reasoning and kind of dividing tasks into different subtasks really helps with long context tasks. And we'll get into each one of these in detail, but kind of the collection of this medical specialization is what embodies the family of Med-Gemini models. So at just like a very high-level glance, how did Med-Gemini do? We found that with these specializations to these frontier models, if we look at a broad range of tasks, we look at 14 different medical tasks for each one of these capabilities, Med-Gemini did very well across the board, achieving state-of-the-art on 10 out of 14 of these benchmarks. Whenever we could make comparisons with other frontier models like GPT-4, we were also able to outperform those models. Of course, medical benchmarking is just one part of the story. It's important. We need to make sure our models have that knowledge, but it doesn't kind of tell us how the model is going to do for clinical utility, actually, like in the actual clinic. So we also looked at real-world applications, things like medical summarization, kind of generating doctor referrals or simplifying abstracts in layman terms, these tasks that could be useful. And we also compared those with clinicians and found Med-Gemini to be performant there. But also, other than just Q&A, we know that having these conversational abilities can really help. So, we want to have the ability to ask follow-up questions and really understand the medical artifact that we're dealing with. Med-Gemini also has these multimodal medical dialogue capabilities that Wei-Hung will get into, and even having conversations with medical videos. So we thought that was exciting real-world applications. I'll be talking about what we did in specific to advance Med-Gemini's clinical reasoning ability before handing it off to Wei-Hung to talk about multimodal and long context. So the challenge here is that a lot of the data sets, these supervised data sets, have a question and an answer, right? For example, MedQA is a famous one. It's in the medical domain. It's a data set that has lots of questions mimicking the US medical license exam, kind of just testing broad medical knowledge. But we have the questions and the answers. But we want to improve these models' ability to reason, to kind of explain why it gets to the answer, but kind of getting that data is very expensive. So that was kind of the biggest challenge we were facing. So we were really inspired by methods such as STAR or self-taught reasoner, where what we do is we start with expert demonstrations. So we curate maybe 5 to 10 examples where we have a question and we have an expert demonstrating exactly their reasoning path, the reasoning trace on how they get to the last answer choice. And then using those examples, we put them in context, and then we generate the reasoning traces for the entire training set, right? And then we do some filtering. So the ones where we get those correct, we keep those in our training data, and then we self-train. So it's kind of like, think about it like we bootstrap from a few demonstrations of reasoning. That was great, but we found out that when we were trying to curate these demonstrations, the experts were using a lot of web search. And it's really important to make sure you have the up-to-date knowledge, and also you might not have everything in your memory or in the model's parameters. So using tools and having this agentic framework where you can also use web search, we thought would be very important. So in addition to the data set where we just have reasoning traces, we have a data set where we have the question, some search results related to that question, and then reasoning traces that kind of showcase how to include those search results in the reasoning themselves. So we augmented this data set to not only have the clinical reasoning, but also integrating web search. We were getting search results for every question. Med-Gemini was answering the questions, but we realized that kind of the improvement in performance wasn't what we were expecting. And we kind of saw that a lot of the times when maybe Med-Gemini would get a question correct, and then we add search results, it would flip to an incorrect question. We found out that was specifically happening when Med-Gemini was like easier type of questions that Med-Gemini should be confident in already. It seems like when we'd add search results, that would maybe further confuse the model. So you don't want to always just add any information in the context, because that can cause further confusion. It can pick up incorrect things. It's kind of like for us, when we overthink something that we already know, we might actually just get it wrong. So we realized we had to be a bit more targeted at inference time. We didn't want to just add search results for every single thing. We just want to add search results for the really tough questions. So that's what led us to also develop this inference-based algorithm. And here's going to be just a video that steps through this algorithm. So we have Med-Gemini, we ask it a question, it gives us an answer, and we do this multiple times in order to get an estimate of the confidence. We can get an estimate of the confidence by seeing if there are conflicting answers. from the conflicting answers, we can generate search queries and then use the search queries to get search results. And then we add those search results in Med-Gemini's context, and we repeat this process. So if we were already confident, we wouldn't enter the search loop. We only enter the search loop when there are conflicting answers. That's kind of like a proxy to the confidence. So with these two things combined, that's what gave Med-Gemini improved clinical reasoning to have these reasoning traces and use web search in a targeted way, which is what allowed us to set a new state-of-the-art on the MedQA test set. But interestingly, like while we were looking into this...
But there's a question.
For generating the conflicting answers, like you change any of the hyperparameters like temperature or something, or is it exact?
Yeah. So we actually found that it worked out very well to just ask the question. You would need the temperature to be a bit high in order to make sure it's not like too deterministic. We found that by just simply doing that, kind of like the self-consistency type setting, it was a really good proxy for confidence. So if we just used kind of that as the technique, the accuracy could drop from let's say you have 90% accuracy, and then you looked at the ones that had low confidence, they would drop to like 50% accuracy or something like that. So just that simple technique of asking the same question multiple times and seeing if the answer is flipping among the responses, that was a good proxy.
I'm curious if you could do something like the entropy of like the token generating like probability distribution instead of having to sample so many times or run through the model so many times as a proxy for search.
Yeah, I think that could also work. Empirically, we found that just asking it more than once gave a better proxy when filtered.
If you're trained like performance, like that, I mean, you have to run through a lot of inference in order to do this. But if you're using the entropy, you would only need to go through inference once, right?
I'm not exactly sure why, but empirically we found that doing it in this self-consistency setting gave a better proxy for confidence. But you're right, it's a trade-off with more inference time and compute.
You're evaluating these automatically, right? Or are you having like hand labeling determining whether they're correct or not on I guess like the confidence interval sections?
Yeah, automatically. So we look at the different answers. So that's because in this case it's say multiple choice, and then we kind of have an estimate of the distribution over the answers, and then the confidence score is just the entropy over that distribution of answer choices.
No, I mean for example, in this MedQA you have A, B, C, D, right? But that doesn't necessarily correlate to what's inside the answer. So I could have A, and then I could have like content of that text be completely separate. Maybe it's the answer choice for B. How are you ensuring that your answer that they're giving is basically the same if you're automating it?
We actually force the model to output A and the content of A, or B and the content of B. So that's how we can always map it back to the answer choices.
So does it have to be semantically the same answer, or like, yes, you go through the NLP, again you analyze all the answers?
We're looking at the consistency based on the answer choices, which would be also the semantically the same.
In your uncertainty guided search inference framework, you are addressing these multiple choice questions. How can you modify this framework to work for maybe like open-ended questions where you generate a response instead of multiple choice questions? Because I guess like two open-ended questions, if you open-endedly answer the question, it can be slightly off, but it's not exactly wrong. How would you assess that?
By using another LLM or a model to tell you, are these different answers very semantically different? And that gives you an idea on is it kind of moving around between different answer choices, even if it's open-ended.
So for like fine-tuning, like you do like compare with like any kind of like RAG kind of approach where you provide the additional context for medical data and see if that improves the result.
I guess this is in a way retrieval augmented generation with the self-training, kind of like. So when we generate the search queries and get the web results, then we're putting that in the context of the model, to then answer the question again with the search results.
I was asking like just like the default Gemini with like the right context. If you like compare that with like after fine tuning.
Oh, I see. Like, what is the kind of ablation of doing the fine tuning versus just doing retrieval augmented generation? Yeah, we have that ablation in the paper, and we found that it helped when doing the fine tuning. And my guess to why that is because some parts of the search you kind of want to ignore. So if you're in training time, you know the right answer. You can kind of train the model to also deal with the search results and ignore the irrelevant information. So we found it helped for that reason. Yeah, so we realized also because we're kind of curating some of these expert demonstrations, and we realized some of the questions in the train set kind of would be referring to a figure, or and the figure is not there. It's a text-based evaluation. So there's like missing information, or like we'd be very confident it should be one answer, but it's the ground truth says it's another. And so since Med-QA is like a fairly popular benchmark in the medical domain, we thought let's make sure that like our improvements over our previous models weren't just in the noise, and in the label noise. We also kind of had this contribution of doing a careful relabeling of the Med-QA test set. For each question, we had 3 different clinicians actually answer and tell us like, hey, do you think there's missing information here? Okay, given that this is your answer, if we told you this is the ground truth answer, is that going to change your answer? So like kind of a proxy for ambiguity. And we found that actually 7.4% of the test set in Med-QA isn't really fit for evaluation because there might be missing information and things like that. So that was a helpful data set that we also released, because then you can kind of make sure you're not looking at those ambiguous questions to see the gains from your method. That was one of the contributions as well. Other than Med-QA, of course, we were interested on how it could generalize to other benchmarks. And we also did very well on this other benchmark called NEJM diagnostic challenges. And gene touring kind of is like testing the genomic knowledge of your model. So we also looked at those two. But yeah, just kind of to recap, we found that this kind of training-based algorithm is kind of inspired by STAR, but also using search, and also this more targeted search at inference. These two combined are what really helped us kind of fill in these gaps for Gemini to make it do well on these benchmarks. But yeah, with that, I'm going to pass it to Wei-Hung to talk about multimodal.
So for the next part, I'm going to talk about the multimodal understanding capability of Med-Gemini. And as you know, like the multimodality is now like a standard. So yeah, multimodality is a very important like component of the modern large model, and also like it's very important key component for the Gemini models nowadays. So given that the medical data is multimodal by nature, so as you know, like we have text, we have image, we have video, blah blah blah. So we're thinking about like how to leverage the multimodal capability of Gemini and try to use that for the medical domain. Actually, this is not the first time we're trying to like do this kind of multimodal medical problem, deal with this kind of problem. So back in like last year, like we have the MedPalm-M, which is like built on top of the Palm-based model, which is the pathway LM. So that's our previous effort, and we got some like state-of-the-art performance on using that model. And this time, like we're trying to build on top of Gemini, and then using the instruction tuning on the Gemini Pro, and also using the prompt engineering on Gemini Ultra to see whether we can make it better. And with these kind of recipe similar to the MedPalm-M, and also like using the similar like fine-tuning data set, we found that we can be like on par or even outperform like a lot of like state-of-the-art method like MedPalm-M or GPT-4V across most of all of the multimodal benchmarks. So not only including for those like specialty tasks that people are usually used like for dermatology, pathology, or radiology. So this time we also include some like general medical domain data set. For example, like the USMLE medical multimodal VQA or like MMNU data set, and also like New England Journal image challenges data set. So we see that our Med-Gemini can outperform other benchmarks pretty well on these kind of benchmarks. And one thing I want to mention that New England Journal Medicine image challenges is like a image data set that has like around 1,000 image.
I have a quick question about benchmarks, right?
Yep.
So you mentioned like how you benchmark this. I'm curious, maybe you didn't have incentive to do this, but like if you modified open source models to like, to be multimodal in the same way that you did Gemini, what would the improvement have been? And like, is there potential there for people who aren't at Google or like?
Yeah, that might be possible. For example, like if you, so right now, if you have like Llama 3.1, you can also try something similar like this. But just need to make sure that like all the benchmark, the task setup should be the same, and the data set that's split, you need to make sure that it's like comparable, and then you can compare with like GPT-4 or like Gemini, Med-Gemini result. So although like Med-Gemini or GPT-4, these are like closed model, like you don't have the access to that, but like you still for some models you can still like using API and try it a bit, like to do some reproduce the result.
For your New England Journal of Medicine challenges, were you just giving it the image, or were you also giving some context, clinical context?
So the New England Journal image challenges is mostly an image, and like it's actually like a MCQ problem. So given an image and very short like case description. So sometimes it's like a 45-year-old male with some problem, and here's the image, and what's the diagnosis? And you need to pick up one diagnosis from 5 options. So that's the setup in this New England Journal of Medicine's challenge columns, like in every like New England Journal in this journal. So the readers can like vote for their correct diagnosis, and for next issue, like they will release the ground truth and see like whether that's correct or not. But basically the text part is pretty short, and sometimes it was just only like what's the diagnosis or something like that. Yeah. So this is different from so there's another New England Journal task, which belongs to the text part. So that's like a very long New England Journal case challenge part.
Be very careful with the case challenges. I'd be very careful about those, because sometimes they will have, from a clinical perspective, a lot of information on there that straight up answers the question beforehand.
Yep.
But if your image and text is that shorthand, perfect.
Yep. Okay. Thanks.
So does the benchmark come directly from published articles? Because I mean, I imagine these models are trained off everything they can get that's been published.
So that's something that we have like also like discussed with the internal like Gemini teams or something like that. So we were sure that our data set, like dermatology data set or like pathology data set, so these are not included in the pre-training phase. So basically the Gemini pre-training, they haven't seen these kind of data before, but some of our data sets are like used for fine tuning, and some of them are not used for fine tuning at all. For example, for the New England Journal data set, so this one is the pure OOD data set in our eval task. Yeah. Yeah. So this is our like we try to benchmark our Med-Gemini from the multimodal perspective, but as you know, like the benchmark tasks are usually not really clinically useful, so the doctors won't use that for like daily use, like, oh, I want to know like what's the diagnosis of this image or something like that, without very
So I'm trying to understand the real world applications of this particular benchmarks and model methods, right? Is this something where it's most relevant for like a radiologist or primary care? Who would be the ones who would be directly mapping to the real world? I'm a patient, I'm going to see my primary care physician. Would this be helpful?
I would say like, so the benchmark data set, so the setup of these kind of benchmark is mostly for the researchers or to compare between different models. So our goal of like demonstrating these benchmarks are mostly like trying to make a fair comparison between Med-Gemini and ChatGPT, GPT or like BenPalm or something like that. But this is not actually the doctor's daily practice or something. So that's why we want to move on to the next part, which I think it's more relevant to like the real world use case, which is the multimodal dialogue capability of the Med-Gemini. So in this application, we combine the Gemini's conversation capability with our medically fine-tuned model and demonstrate like the Med-Gemini can actually do like multi-turn medical conversation with the user. So you can see that example. So that example is a user that has the skin condition, the medical concern, and the user is asking like Med-Gemini, like, what's the diagnosis? What should I do? So interestingly, like when the user just inputs some like short description about the skin lesion or something like that, the Med-Gemini didn't output the diagnosis directly. Instead, it asked the user to provide the image first. And after collecting enough information, the text and also the image, and it will give you and with some asking some history, it will give you like a diagnosis given that image and all your description. Med-Gemini also answer all the follow-up questions about like what's the reasoning of that differential diagnosis, what's the explanation, and what's the treatment options for these kind of problems, given like patients' follow-up question. Even though this is just like a preview of the Med-Gemini capability, so we didn't do like a very thorough study and evaluation framework for these dialogue capabilities, but we are working on that right now. And but with this like preview example, you can see that there are some potential opportunities of like using Med-Gemini for the real world use case, because you can imagine like if you have these kind of assistant in your phones, or like the doctor have these kind of phone that like you can easily reach out to this.
I wanted to ask, so for your multi-turn conversations, because Gemini has such a long context, for each turn of the conversation, do you ship all of the previous context back into the model for inference at the next step, or is there like maybe a way you can choose the important information from the previous context so you put it back into the model to do inference for the next step?
In our case, like we can just use the previous chat history, but you can imagine like because this is like some experimental stuff. So the history is not that long, so it's easy to just do that. But the other way is like if you are a long-term user and you have a lot of like patient information, patient history already saved somewhere in the server, so maybe an ideal way is like try to do the summarization on top of your chat history, and then use that to be a background for in-context learning or something like that. And then on top of that, then you can ask more questions.
What if diagnosis is not correct, or even if it's correct, but user thinks that it's not correct, right? And like, did you guys think about liability aspect?
So that's actually something different between the research and the product. So for research, of course, like we can demonstrate, like we can push the boundary, like okay, we can do this, we can do that. But for the product, we need to be really careful. Like so. That's why, like, after we demonstrate that, we actually ask the real doctor to see what's their feedback about like these kind of demonstration. So yeah, just like you mentioned. So the doctor, so this is the skin condition case. So we asked the dermatologist to go through this example and also other examples, and the feedback we got, the good thing is that it's pretty impressive that Med-Gemini can get the accurate diagnosis with like photos and the descriptions, and also like give you like a very thorough like therapeutic opinion, like options or something like that. But they also suggest that, before reaching the final diagnosis, it's better to gather more information to make sure that the diagnosis is more like conditioned on like what's the real problem, the real the demographics or something like that. And also, it's good to have a list of differential diagnosis instead of just one diagnosis. So that's what like the doctor usually do in the real clinical role, right? So we start from we listen to like the patient's complaint and asking some question, and then we come up with a list of differential diagnosis, and then we start ruling out the diagnosis inside that list based on all the evidence you have seen later on, like the lab test or something like that. So it's good to have like a list of differential diagnoses instead of like just one diagnosis. Yeah, so that's true. And for the legal and for the real world product things, I think that's very important. Like at least you need to show that how much confidence the model will have for given these outputs.
Yeah.
You know, like when it comes to disease diagnosis, you have ICD-10 codes and ICD-11 codes, which are a formalized way of saying that, okay, this is the disease, right? So have you kind of benchmarked on the space of ICD-10 codes or 11 codes, trying to figure out in which of these codes is the accuracy really high, or in which of these ICD codes is it particularly low accuracy or more vulnerable to adversarial perturbations or something?
Yeah.
Do you have any insights into that?
That's a good point. So in our study, we didn't do the ICD code mapping things. So we completely do this in the free text format. But I think like your idea is pretty good. Like mapping these to ICD code, you can somehow understand like what kind of disease or what kind of category the model can do better, or what kind of category the model will have some issues or something like that. For example, like if we train our model with a lot of like cardiology data or something like that, then we might expect that the ICD code belongs to cardiology, it might perform better. And if we don't have like the MSK data, then we might expect that for the musculoskeletal disease, it might perform not good, not that good. So that's like something we can improve in the future. So yeah, like mapping between text and ICD code, or even like you can do some like graph learning or something within the ICD code, because there are some like relationship between different ICD categories, right? So that might be something we can explore more.
So another question here, sorry if you don't mind. So I think the elephant in the room is what's the motivation behind having a foundation model in the first place? I think that has become the go-to approach for a lot of things recently. But why even have a foundation model, right? Why not just have a bunch of specialized models, for example, that perform much better on each of these individual tasks?
Yeah, that's actually a good point, because I actually put that in my limitation part, and that's something that we don't have consensus. Maybe we can go back to this point later, but yeah, so there's like a debate between like generalist model versus specialist model. Yeah.
And I'll also add to that, it's a great point. I think a nice thing about these foundation models as well is the conversational ability and being able to maybe upload different types of artifacts and have that back and forth. Perhaps with a very specialized model, you lose that capability maybe, unless you're also thinking about plugging in multiple specialized models into an LLM, or having an LLM be more agentic where it kind of queries a specialized model to get the diagnosis and then has a text-based interaction that way. So those are both interesting questions.
My follow-up to that would be, why are we doing things that are conversational? I think, is it a question of we think chat is the best interface, or is it because the best thing we can do is next token prediction and we forced everything down that path? And the end result is just chat, and now we've all converged, and we said, hey, by the way, chat is the best way to interact.
Yeah, also a great point. I think that the reason why is kind of history taking is one of, having conversation with a patient is one of the most central medical tasks in a way. That consultation with the doctor and being able to ask those follow-up questions. So that could be one reason why you want to do that.
The user experience, I think.
So in the medical domain, what's the difference in terms of model performance, like between medical foundational models versus like specialized training models?
Medical foundation model versus specialized.
Yes, specialized.
So the foundation model, you mean like Gemini versus Med-Gemini?
More like
Traditional.
Or traditional one?
Yeah, Med-Gemini versus like the traditional, like non-LLM.
Yeah, so that really depends, and that's actually a very good question, because that's also like go back to the question about like whether the generalist versus specialist, which one is better? And usually you can see like for some tasks, Med-Gemini is actually not the best one. Like later on, I'll show you like there are some tasks like the traditional, the supervised model. It's old, but it performs really good. Like even like Med-Gemini with like so we try different kind of technique, but still there's still some gap over there. Yeah, so that really depends on like what kind of data you included in your pre-training, your fine-tuning, and whether this is like a very niche kind of modality or something like that. Yeah, so I would say specialist model is still very valuable. It's small and it's like you can iterate fast and usually perform pretty well if you have a very specific task target. The third part is about the long context processing of Med-Gemini. When I saw this like long context capability of Gemini 1.5, I feel like super excited because with this kind of long context capability, we can actually now like working on let's say like 2 hours video, so it means that equivalent to like a movie or something like that, or like a textbook with like millions words or something like that. So what does that mean for medical domain? So for medical domain, like with these kind of super long context window, like that means that we can start like working on long documents, for example, like electronic health record note collection or something like that, or like medical video, surgical video that usually take like 30 minutes, 1 hour, or even longer. Or even like if you want to learn some new task during the inference time using in-context learning, this become like more possible than before. And so that means that you don't need to include everything into like a pre-trained model or like a fine-tuning most of the time. So these kind of long context capability actually like unlock different kinds of tasks that cannot be done before. So or even like GPT-4V because its context window is smaller than us. For example, like I'll talk in more detail later, but for example, like needle-in-a-haystack context retrieval for EHR, or like a literature review or surgical video understanding. So all these tasks become possible with this kind of long context capability. So the first example is the needle-in-a-haystack retrieval for EHR. This problem setup is like this. So for each case, each clinical case, each case has like more than 100 nodes, and this node collection is super long in total, like 200K to 700K words. We also give like a medical condition that only mentioned once across the whole node collection, and we ask Med-Gemini to whether it could be possible to find, identify whether this case has this specific medical condition. So we use the two-step chain of reasoning approach to try to approach this problem. So what's the two-step chain of reasoning means? So the first step, you can see in the right, the font is a little bit small, but yeah, the first step is trying to retrieve the mentions of that specific medical condition from the whole node collection. So let me take an example. So if you are interested in a case, whether a case has a problem of hypothermia, which is a low body temperature problem. First, we will ask Med-Gemini like whether can you help me like retrieve all the mentions about the hypothermia or low body temperature within all these like 100 nodes, and then Med-Gemini will come up with a list of the dimensions, probably including like the actual hypothermia words and also like some numbers of body temperature or some symptom like chillness, shakiness, or something like that. And with this list of mentions, we ask Med-Gemini to do the second step, is to decide whether the medical condition actually exists in this case. So this is based on that a list of mentions, and then derive from there to make you to give you like a final answer, like whether it's yes or no. We found that we used the Med-Gemini with just like one shot example, and the performance is actually on par with the very like carefully tuned state of the art, just like you mentioned, the very traditional way. So that state of the art is like carefully fine tuned, and also it's like based on the expert's heuristics. And we found that the Med-Gemini with one shot is like on par, and the F1 score is around like 0.77 to 0.78. So both precision and recall is around this level. So we found that this is very impressive and very good performance. And the second example is actually one of my favorite one. So it's a literature review and summarization capability. So if you're a researcher, I suppose that you need to do a lot of like literature search, literature review, and come up with like a short summary or something like that for your paper. And Med-Gemini, we use Med-Gemini to do these kind of tasks for us. So in this example, like we want to know like whether if I'm interested in a gene called FTO, and we are interested in the mechanism between this FTO and obesity, and we found like 12 papers about that. So we just asked Med-Gemini like, okay, so what's the mechanism between this FTO gene and the obesity, this symptom? And we gave Med-Gemini, uploaded 12 papers, and then asked Med-Gemini to like give us like a very organized and structured summarization. And from this example, you can see Med-Gemini can actually give you like a good summarization in a like itemized point, and also like pull out a reasonable like experimental support from like 12 papers. Of course, you need to read the paper later, but it can give you like a good summarization. We think that Med-Gemini, with this kind of capability, it's possible for the researcher to like do this kind of literature review faster and keep updated with like tons of archive paper every day, and to accelerate their scientific discovery. Yeah, so that's the text part. And the next part, I want to show you a few examples about like using Med-Gemini for the video understanding. So the first video example is the medical visual answer localization. So the setup is like given a video and a question related to a segment of the video. We want to identify the start and end point of that segment, specific segment. So there is a benchmark data set called Med-QA. It's actually set up like this. And we found that with two kinds of setting, like just using video or video plus the subtitle. So Med-Gemini are both like outperform the non-language model state-of-the-art method. So we haven't tried other LLM because for GPT, this is like too long, so it cannot be fed into GPT. Yeah, but basically, the Med-Gemini can outperform the state-of-the-art.
Against non-medical models, like for this particular task, or for a lot of these tasks, like how would they perform against non-medical models? I'm quite curious because.
You mean the performance gain?
Yeah.
So for this one, it's specifically good. So it's like a 50 something.
No, but that's Med-Gemini against like a state-of-the-art model for that healthcare-related problem, right?
Yeah.
Like Gemini versus Med-Gemini.
Oh, okay. So that part we haven't actually do that.
Yeah, I think with those natural kind of more videos, I would guess they're similar. Yeah. I think Med-Gemini have better performance on the more medical domain stuff, like the surgical videos that are gonna come next.
Yeah, like this one is more like a natural scene, but the next one is more like a surgical image. So for this one, you might expect that there might have some gap between generic Gemini versus Med-Gemini. So this one is kind of similar. This example is also kind of similar to the previous one, but it's trying to identify the surgical action second by second, given the video. So we asked like Gemini to like help us annotate like whether this specific second the operator is working on like cutting or suturing or tying or just doing some background action. We have the surgeon in our team like go through some result, and it's pretty promising. But also like our surgeon point out that sometimes the Med-Gemini might get a little bit confused about like the suturing or tying annotation, because there might have some like definition overlap between these labels. Of course, like we might need to like do more like prompt engineering to make sure that the language model can actually understand those nuances, or like try to even improve the foundation model to make it better to detect those like a fine-grained motion or something like that. So that's still like some ongoing research. This is the final example, so about the surgical video. So this is a real-world use case. So if you're a surgeon, like when you like doing the laparoscopic cholecystectomy, which is the gallbladder removal surgery, like there is a useful like criteria called critical view of safety (CVS) criteria that you can use to decide whether your surgical view has like exposure enough of anatomical structure so you can like mitigate the risk of bioduct injury. So that's the goal of this CVS criteria. In the real world, like the surgeons, they use this CVS criteria during their operation and make sure that everything like needed is like shows up in their like surgical view. And for Gemini, like we fed the laparoscopic cholecystectomy video into the Med-Gemini and asked Med-Gemini like whether this whole video like actually meet these criteria or not. So this is a classification problem, like whether this surgery like achieved or partially achieved or not achieved these criteria. So for this example, just like we mentioned, like the supervised state-of-the-art model actually performs better than Med-Gemini, but we also compare Med-Gemini with GPT-4, and we found that there's a 21% better than GPT-4, and it's also like just using a subset that can be processed by GPT-4v. So we still think that even though it's not as good as a state-of-the-art like traditional method, which is using the ResNet 3D or something like that, specifically like fine-tune on these kind of surgical video, but we think that Med-Gemini just using like one-shot example and still get these kind of performance, which is like 10% accuracy difference. We think there still have some space to improve based on this application. So the final one is we can combine the conversational capability with these kind of long context surgical video understanding, and this can be very helpful to have the Med-Gemini as an assistant for the medical education. Let's say you are a medical student and you want to know whether this this surgical video actually performs pretty well, like it exposes like all the anatomical structure you need during the operation. So you can ask Med-Gemini like whether this is a good quality surgery and what's the good part, what's the bad part, or something like that. So these kind of interactive learning experience will be very useful for the medical education. We've talked a lot about the capabilities of Med-Gemini, and so these kind of capabilities can enable us to like come up with some new ideas or some potential good novel applications. For example, using the conversations or like a literature search or like or etc. So there's a lot of good things we want to share, but also there's a lot of limitations in this study. So the first thing is that even though there's like different kinds of you saw a lot of different kinds of complicated real-world applications, and we show you like some previews and example over there. But for these tasks, there's still like more work we need to do. For example, like we need to have a rigorous problem formulation and also building a robust evaluation framework to make sure that Med-Gemini can actually work well on those tasks and also not behave like bad, like generating some hallucinated response or something like that. So that's something we're still working on, and we hope that could be improved in the future soon. And the second limitation is that there's no convergence between the generalist and the specialist model. So as you know, like everyone wants to build a generalist model, like unified model to solve everything. But apparently, like these kind of model is usually huge and it's slow iteration, and usually the performance is not as good as the specialist model in some specific. If you have a very specific task, then maybe you can go for a specialist model and just focus on that task. But we would say like both kinds of model have its own value. So we'll keep like iterating on improving the generalist model and the specialist model, and just based on what the outcome and the output, what kind of things you want. So this is the final slide. And in summary, like we go through like the Med-Gemini capability through like three aspects. The first one is the clinical textual reasoning with self-training and search integration. And also we talk about the multimodal understanding and long context processing. capability. And we'll also show you that Med-Gemini can demonstrate the state-of-the-art performance on different kinds of benchmark, and also we show you some real-world application that can be inspired or maybe can be used in the future in the real-world applications, like the conversations or scientific discoveries or like education purpose. And finally, we have this full relabeling MedQA dataset, which is open source for the research community to do the robust evaluation if they are interested in using the MedQA dataset. And here's our paper link and the GitHub for that dataset. So that's it. So thank you.